Let's learn how to graph complex numbers. A complex number can be expressed in the form a plus bi, where a and b are the real parts. So in this case, 3 and this 4 is our real part. And then this I right over here is our imaginary part. I is equal to the square root of -1. Now the 4 itself is real, right? But when we multiply the real part by the imaginary part, then we get this imaginary part. So b itself is a real number, right? But then when we look at bi is actually imaginary, but b itself is a real number. So you can actually think about a plus bi as a being the real part and then bi being the imaginary part. And we can graph this on a coordinate plane. So just like how you would graph things with an x and y axis, let's just do it, except you have a real and you have an imaginary axis. So on your x-axis is going to be the real numbers. So say we have 0 here. It's just 1, 2, 3, -1, -2, -3. On your imaginary axis, you have I, 2i, 3i, so on. And then down here you have -i, -2i, -3i, and so on. So you can kind of see the pattern here. Let's say if we're asked to graph a complex number, which I'll use the variable z to represent. So let's say if we have a complex number z, and the complex number z is in the form of a plus bi. So in this example, we're using 2 plus 2i. So how do we graph this? Well, this 2 right over here represents our real part, and then this 2i represents our imaginary part. So what you're going to do is you're going to go 2 in the real direction. So you're going to do 2 in this direction. And then this 2i right over here tells us to go 2 up in the imaginary part. So this point right over here would be 2 plus 2i, right? You have this 2 here right over here representing the real part. And then don't forget the 2i part. So, we have to go up by kind of 2 units, right? So 2i is right over here. And there we go. Z is equal to -1 minus I. Well, if we were to graph this, once again, the -1 represents our real part. The -I represents our imaginary part. So it's going to be -1. So we're going to go 1 here to the real part, right? So we're going to go kind of -1 in the real part. And our imaginary part is -I. So our -I is located here. So we're going to go 1 down, right? So you go 1 to the left and then 1 down because that's where -I is located. And we're done. All right. So if we have like an imaginary number, let's just say 34 plus 38i. Well, what you would do in this case is 34 is our real part. So we're going to go 34 this way, right? 34 this way. And then this 38i is our imaginary part. So our imaginary part is represented with the y-axis. So in this case, we have to go 38 units up. And that's where 38i will be. So yeah, that's kind of how you graph complex numbers. Might be wondering, well, why is all of this important? And the reason why graphing imaginary numbers is important is because you kind of get a visualization for what I really is. Now, I is equal to the square root of -1. Okay. But you can, from now on, maybe start to think about I as a rotation. So you're rotating something by 90 degrees. What do I mean by that? Let's take the number 1. So let's say if we have the number 1, right? And I multiply 1 by I. I'm just going to get I, right? Because 1 times I just gives us I. So I is right over here. Notice how I make a rotation of 90 degrees. If I multiply I times I times I is equal to -1. -1 is located here. So I times I gives me -1. 90 degree rotation. If I multiply -1 by I get -I, 90 degree rotation, and you kind of see the pattern. So they're also useful for visualizing the solution to all sorts of equations. If we have the equation x to the third power is equal to -1, it turns out that the solutions for this equation actually form a triangle. I'm not going to go too into detail about that, but it turns out that they form a triangle on the complex plane. And we'll be exploring why. And it's actually an equilateral triangle. So not only are they forming a triangle, it's not just any sort of triangle, it's an equilateral triangle. So all the sides are the same length. So all of these points are equally distant from each other and all the angles are the same. So that's something that's also interesting. You can also use this information. To find out what the absolute value of a complex number is. A plus bi. The absolute value of a number. Let's say if we're trying to find out the absolute value of -3. Well, let's see. Absolute value of a number just means how far away is that number from 0, right? How far is that number away from 0? So if I graph -3 on the complex plane, notice how it's just 3 units away from 0, right? So the absolute value of 3 is equal to 3. If we have something like the absolute value of, let's say, 3 plus 4i, what is this going to be equal to? Well, we know that the absolute value of a number is just the distance that number is away from 0. So if I graph 3 plus 4i, let's just say this is 4i. So 3 plus 4i lands us right up over here. And because I'm taking the absolute value of it, this is just the distance from that point to 0. And, notice how this right over here forms a right triangle. This length right over here is 3. This length right over here is 4. So you can think about the absolute value of a complex number as just trying to find the length of the hypotenuse of this right triangle, right? Because we went to 3 and then we went straight up. So this is going to be perpendicular to the x-axis, right? Went straight up. So defining the hypotenuse of a right triangle, a squared plus b squared is equal to, let's just call this c. So this length is c, so c squared. We have, that's 16 plus 9, that's 25, is equal to c squared. And then we have c is equal to, if we take the square root of both sides, we have c is equal to plus or minus 25. Plus or minus 5, sorry, square root of 25. It's plus. But the thing is, this length of the triangle right over here, it's positive, right? How can this be negative length? So our length right over here is 5, which means that the absolute value of 3 plus 4i is 5.